Alright, so right now I have division and shrapnel mine, or some portion of what might eventually become shrapnel mine, next to each other. And you can see there's very different, everything about these bots is very different. And the reason I'm showing you this is because not every robot's the same. I mean, not every robot has the same needs. And I think at the end of the day, what a lot of you are watching this video to learn is, how do I pick a motor, a speed controller, and a battery for my robot? And the answer is, it depends. I can't give you one answer because not all robots are the same. It would be stupid of me to be like, every single robot should use this motor for both the drive and the weapon, should use all identical 35 amp speed controllers, and should use this 2-cell battery. Because that's dumb. Not every robot has the same needs. What are the needs of this robot that make it different from this robot that made it so that I chose different motors? Well, I'll tell you, and I'll use these robots as a use case for each of these motors. And I'm not going to tell you what to do for your exact robot because I would be here all day answering hundreds of questions from everybody about their very specific robot, and I simply can't do that. What I want to do is give you a better idea of what do you need to know to make these choices for yourself.
Hey there, this is Seth Schaefer from Team Just Cause Robotics. Today's video is going to have a lot of different things crammed into one video. In general, what I want to talk to you about is electrical component selection. I won't talk about how to pick just the right motor, battery, or speed controller for a given robot, however. I've covered those in my spinner design and drivetrain design video series, which I'll link below. Today, I want to talk primarily about what all the specifications and numbers on each component even mean in the first place, how to pick a full system of parts that will work together, and how to make sure that when you plug everything in for the first time, it doesn't blow up. In the combat robotics world, we use a lot of the same exact electronic components that are used in other robotics projects, RC cars, planes, and drones. These all have a ton of numbers on their product pages and specification sheets, and I want to break down what all of these mean, and how you can choose the right parts to ensure that your project or robot won't blow up. I'll also briefly talk about how a lot of these ratings could be misleading or just downright lies, and what you should be looking out for. I'll also show examples of a couple different products that do the same thing or have similar ratings, and what the differences actually are between them functionally. This will add useful context for my next video, where the focus will be on the product development work that I've gone through to develop my very own parts just for combat robot builders. I've spent over a month now working on developing and then making and selling a small batch of power distribution boards for combat robots, and you can buy the last few of them right now on my web store. I'm planning on putting together a large batch order soon, so these will be available in a more polished form for years to come. But you'll have to stick around next time for that, so make sure to subscribe and hit the bell icon to get notified when that video drops. And if you have any questions you want me to address in the next video, leave those in the comments below.
First off, let's talk about batteries. Batteries are perhaps the cornerstone of all that we do here in combat robotics. They come in all shapes and sizes, but generally when we're dealing with combat robots, we're going to focus just on the type that are known as lithium polymer batteries, or LiPos, L-I-P-O. So all of these here are different lithium polymer batteries, obviously all different weights, all different shapes. These two are both ones that I have at least at some point used in Division, whereas this is what I currently use. This is what I'm planning on using for Shrapnel Mine. You can see all of these are Tatu brand batteries. And I have a random 2S that I might use at some point for a smaller 1-pound robot. And this is the 6-cell battery that I use in my 12-pound robot Draconid. So why are these different shapes and sizes? What do all the numbers mean? Well, I went over this in more detail in my older electronics tutorial video, which is one of the first ones I ever made. But briefly, the numbers that are important here are the number of cells, the voltage, which is just a multiple of the number of cells, and the capacity, which is in milliamp hours, and is this number right here. And then we also have, of course, a discharge rating. So on this battery, for example, so this, I wrote the number 1 on it, so it's kind of covering some stuff, but this is a 650 milliamp hour battery. That is the capacity. It is 0.65 amp hours, or 650 milliamp hours, however you want to say it. 75C, which means that it can discharge 75 times that capacity in amp hours, so 0.65 times 75 amps continuously, though that is probably unrealistically high, and it probably won't actually do that without getting extremely hot. And it is a 14.8 volt battery, because it is a 4-cell battery. You can see here those little polymer bags, which is what makes a lithium polymer battery have its name, are the cells. There's just 4 of them in here. This is a 3-cell battery. It has 3 polymer bags. This is a 2-cell battery. It has 2 polymer bags. Pretty straightforward. The nominal voltage, which is to say the average voltage or the voltage at about a 50% charge of a lithium polymer battery, is 3.7 volts per cell. So 2 cell, 7.4 volts. 3 cell is 11.1 volts. 4 cell, 14.8 volts. Very simple. As it charges and discharges, the voltage per cell will change from about 3.3 volts fully discharged to around, or almost exactly 4.2 volts at full charge. You can discharge them beyond 3.3 volts. I do not recommend it. The battery might explode when you recharge it. Lots of battery safety stuff to cover in there. I'll link an article below. This is a 6 cell, so it is a 22.2 volt battery, and this is generally the largest that you'll easily find, but you can always just wire more of these in series, and that essentially makes it so that instead of 6 cells, you have 12, and then you can do 12S at 44.4 volt nominal. Otherwise, you can see the same kind of deal, 1300 milliamp hours or 1.3 amp hours, and the C rating on this guy is 50C, so it can do 50 times 1.3 amps at once, so more than 50 amps continuous, which is plenty for Draconid. This is the battery that I usually use in Mini Mulcher. You can see here, kind of, at least, that it says 45C/75C. If you see something like that, that basically is supposed to be a continuous rating and a burst rating. So in other words, for some number of seconds, probably less than 10 seconds, it'll supposedly supply 75C, but it'll do 45C for longer. Now, when it comes to LiPo batteries, the C rating is probably the number one thing that manufacturers will inflate and lie about. So generally, I have seen a 75C battery with the same capacity as another 75C battery get way, way hotter under the exact same current load, and that was just a different brand of battery, different type of battery. The one with that was not as hot was also a much heavier battery. So, I mean, there's only so much you can do in such a lightweight package. I would definitely not skimp on C rating. If you know that you're trying to design something that needs a 100C battery and you buy a 100C battery, you're probably going to have a bad day because that 100C rating probably lies. I would say you might actually need to get a higher capacity battery to compensate for that. So even if your robot's only going to draw 50 amps, if you get a 100C 500 milliamp hour battery, that's 50 amps, and it probably won't actually supply that without getting extremely hot. So I would say you might want to go up to like a 650 milliamp hour battery, so you have a 65 amp discharge instead. Now, I already talked about how current ratings are probably the worst part of trying to find a battery, but with speed controllers like these, it's pretty much the same. These are both brushless speed controllers. This one here, you can see the number printed on it is 50A, because this one is rated for 50 amps. This one, 35A, rated for 35 amps. You can also see this literally says on it 2 to 6S LiPo. That means 2 to 6 cell lithium polymer battery can be used. And this one doesn't say, actually yes it does. It says 3 to 6S LiPo. So this one you can use 3 cell to a 6 cell LiPo. So 3, 4, 5, and 6 all work on this one. 2, 3, 4, 5, and 6 all work on this one. The voltage range is just what those batteries output, so these just make it easier for you by telling you what cell count to use with it, because they're meant to be used with lithium polymer batteries, since these are meant for drones. Now, why is it important that these are meant for drones? This is also a 30 amp rated speed controller, so a lower current rating than this one. As you can see, it's a bit bigger, isn't it? Just a little, you know. So this guy, Big Chungus here, or I should say Medium Chungus, about 30 grams. This guy, about 6 grams. Okay, why the hell do these have the same rating? Well, let me blow your mind even more. Big Chungus, 50 amp rating. This one, also a 50 amp rating. This guy is like 60 grams, whereas this one is like 10. So what the hell is going on here, you might be wondering? Well, the answer is lies, and also deception, but also heat transfer. I don't want to get too technical with this, but generally speaking, this guy has a big ass block of aluminum in it, And that connects to some components on this board and components on this board. And there's an even bigger block of aluminum up here that'll act as a heat sink. This allows this guy to dissipate heat very efficiently. These have a sticker up top, and it's like a metallized sticker, but that's all you get in terms of surface area to dissipate heat. And there's like no thermal mass on these whatsoever because they weigh like 5 grams without the wires and everything, if that. So basically, this cannot actually output 35 amps continuously. It will blow up. I measured division at 25 amps in testing, and then I used 35 amp speed controllers with it, and it blew up. That's why I ended up moving to 50 amp ones, and now I've actually moved up to a motor that is rated for 60 amps, and I actually run an 80 amp rated speed controller with a current limit of 40 amps to make sure that it won't blow up. Something like this, you simply cannot physically fit into most BO8s, nor would you want to, because this is a horrible use of weight. I mean, it's freaking gigantic, but this will probably output 50 amps all day long and not blow up. I trust this one. I don't trust this one. The voltage ratings will be accurate, but the current ratings you need to take with a big grain of salt. Now, I'm not going to say this one is actually only like a 10 amp speed controller, because that would be disingenuous. I mean, we're running these for only 3 minutes in combat. They might get hot, but they won't necessarily melt down at 20 amps or whatever. But also keep in mind that with motor loads, they're almost never continuous loads anyway. I mean, with your drive system especially, you're pretty much constantly ramping up and down the throttle on each wheel, and that actually creates current spikes that are in excess of what the motor's rating is for a continuous load, but they're only for fractions of a second, so usually it doesn't really matter. For instance, here on Shrapnel Mine, when I hook my power meter up to this guy and I rev the motors back and forth repeatedly over and over and over again, it spikes at about 13 amps. But if I actually run them continuously at full speed, it draws about 2 or 3 amps with both motors together. And that's with the motors just spinning the wheels in the free air, so when it's actually pushing itself around, maybe it'll be like 5 amps or whatever, but the continuous load is very small. So these 35 amp rated speed controllers are able to deal with it just fine. It's not a big deal because I'm drawing peaks of less than half of their rating, and they're perfectly happy with that. In fact, that was for both motors together, so really each one's peaking at like 7 amps or whatever. So I'm never reasonably, even if I'm pushing like something twice as heavy as this, continuously drawing 30 amps. So I don't have to worry about the fact that this is a 35 amp rated ESC that can actually only output maybe 15 amps for a minute before it blows up. The other issue when you're dealing with thermal considerations is that cooling really matters. So these guys that say that they can put out 35 amps, they might actually put out 30 or 35 amps when they're underneath a drone's propeller that's spinning at full speed, throwing a ton of prop wash at high velocity past them, because that's the intended use case for this. But this guy is meant to be hidden inside of the body of, say, an RC airplane or a boat or something where it gets no airflow because it's inside of an enclosure, and its body is big enough to absorb the heat and dissipate it slowly over time just from the sheer amount of mass that this has and the amount of surface area that it has with the big aluminum heat sinks. So this guy will be able to operate for probably hours at 50 amps, whereas this guy can only operate for mere seconds at 35 amps before it'll blow up if it's not getting a huge amount of airflow. And also, it's not like this is just going to instantly fail at like 20 amps or whatever. It might take a bit to heat up to the point where it fails. And that's where things get really convoluted when it comes to current ratings, because there is no way to say, yes, this will absolutely work, or no, this won't absolutely work. It's very hard to say that unless you're talking really high extremes on one end or the other of the rating. But it might work at first and then die after a minute. It's hard to say, because the thing might heat up the whole time until it just gets too hot and then you're done. Another consideration with the drone speed controllers is they're meant to be used in connection with a flight controller on a drone. And usually those flight controllers will have some sort of circuitry on them or attached to them that will convert from battery voltage down to 5 volts to power your receiver. So with these guys, you usually need something like this, which is a BEC. It says your BEC, that's just a brand thing. A BEC stands for battery elimination circuit, and it eliminates the need for a second battery that is at a lower voltage just to power the receiver by instead supplying 5 volts directly to the receiver. You generally will see BECs rated at 5 volts or 6 volts, and some input voltage. This one I think can go up to 6S, and it will supply 5 volts at up to some number of amps. The current ratings on these are usually kind of bullshit too, but realistically, if all you're powering is a receiver, it will be drawing like 50 milliamps, which is 0.05 amps, and something that's rated at 2 amps will absolutely be able to supply that, even if that 2 amp rating is bullshit. Now let's talk about motors. Motors can also be a little complicated, but they are less likely to just outright lie to you about specs. So this is a prop drive. This is the 2836 3000 kV prop drive. On the spec sheet, you will see that it has a rated voltage range or number of cells. 3000 kV is an actually important number, which tells you how many revolutions per minute per volt. So 10 volts, this will be going 30,000 RPM because it's 3000 kV. The 2836 is just the size of the can-ish in millimeters. Some motors go by stator size instead of can size, so that's not always that reliable. This is an 1806 2300 kV. So this one, if you supply 10 volts, it'll go 23,000 RPM. I run these in division at 4S, which is 14.8 volts for the drive, so they spin super fast, and that's why I need a gearbox to bring the wheels down to a semi-reasonable speed to drive with. This is what I used to use in the weapon on division. This is the can from what I currently use on division. So this is a Cobra Motors 2814 1850 kV. 28 and 28, but this is like a 28 millimeter can, this is a 35 millimeter can, because this one goes by stator size and this one goes by can size. So that's the thing to look out for. This motor, when it's an actual complete motor, I don't have the rest of it attached because it's on division right now. This guy is rated for, I think, 60 amps, and this one I think is rated for 55 amps. But the size of the motor and its ratings don't really have that much to do with each other because it really has to do with the windings, what the actual thickness of the copper wire is, how many turns per stator tooth, how many stator teeth. It's a whole thing. I'm not going to get into that in detail. Suffice it to say, if you're using a motor that's rated for 55 amps continuously, and you're trying to run it with a speed controller that is rated for 50 amps continuously, you might have a bad time if it's actually drawing that. But the current draw of a motor is not dependent on the rating of the motor. The current draw of the motor is depending on how much load you put on it. So like I said with division, I was using this motor and drawing like 25 amps, not 55, because the motor is just going to draw as much current as it needs to produce as much torque as is demanded from it. And if it's demanding too much torque, then the motor is going to draw too much current and it'll get really hot and it'll melt down or burn up or something. As long as you're running at the right voltage, it probably will never instantaneously blow up when you plug it in, and that's not a thing you generally have to worry about. But like with the speed controllers, you're really dealing with the heat dissipation aspect with these guys, and if you can have them next to a spinning weapon that provides some airflow, they might run cooler than otherwise. If you bolt them to a gigantic piece of aluminum like I have on the Vision, they might run cooler than they would otherwise, and you'll probably have a better time than if you bolt this directly to like a 3D printed plastic chassis that then gets so hot that it will start to melt the plastic around it. Here are two motors that are both 2205s with similar KVs. So this one is by Emax, this one is by Cobra Motors, just like the Division motor is. So this guy is a 2300 kV 2205 motor. This guy is a 2600 kV 2205 motor. There is nothing that you could outwardly tell by looking at these that would give you that information. Things that you can see by looking at these though, the magnets on this guy, a lot smaller than the magnets on this guy. This is, I would argue, a higher quality motor. I would hope so too, because I spent, I think it was like $60 to get 4 of these, whereas these ones were around $5.50 each. These are smaller, they're probably a bit lighter, and they're lower KV. 25.66 grams versus 30.41 grams. Or with the cable on there, 31.27 grams. So this Emax motor is what I'm using for both the saw and the drive on shrapnel mine here. You can see it right there. Annoying things with these drone motors is that a lot of them will come with sets of 4 that have clockwise and counterclockwise threaded shafts. You can see this is one of the left-hand thread ones. So they have a different colored nut. And then the other thing is there's these little arrows on the top that point to different directions. So this one is meant to spin this way. So that's the direction that would tighten the nut against the load of the propeller. This one's meant to spin this way, which would tighten this nut against the direction of the propeller. Whoops, because this one is the normal clockwise thread. This is the back ass where it's left-hand thread. So that's one thing to look out for when you're buying drone motors in sets of 4. You'll see CW and CCW for clockwise and counterclockwise. And it's sometimes impossible to buy them not in pairs or sets of 4, like in the case with this motor. So why am I using this instead of this? Well, this I actually don't know the current rating, because like I said, the current ratings are kind of meaningless anyway, but this one doesn't even have one published. So I just went with this because it's a higher kV, and I wanted a higher kV for the saw. And generally speaking, a higher kV motor will draw more current at the same size of motor. Now, obviously these are different manufacturers, and there's a lot of other factors between them. But I've run one of these inside of Mini Mulcher as a replacement for this motor, which is also one that I ran originally in Mini Mulcher. And I found that this has way more torque and quite a bit more power in general. So I'm happier with the performance of this motor than I am with this one, but there was nothing on the spec sheets that would necessarily tell you the difference between them. It's just physically looking at this motor, it's bigger, it has more thermal mass, it'll probably take the heat better, and the shape of them is also different. You can see this one has a much shorter overall can, but it has this like weird little bump here, whereas this one, it's a nice flat surface, which is great because when I'm mounting my saw blade on shrapnel mine, I can mount the saw flat up against this nice wide flange that is the front of the motor, and the saw spinning through the air will absorb some of the heat from the motor can and actually help to cool it off a little bit in the process of also allowing for a much wider surface to clamp this against for a more secure hold in general. Exciting happens here. Yeah, you see that? Little sparky bits shooting out of the DF Robot speed controller there? Yeah, it didn't like that. So what I've got here is one of the Bristol Bot Builders speed controllers that they've just developed to use with N20 motors. So these are designed to basically be a direct replacement for the style that is on these DF Robot motors that I got with the speed controllers pre-soldered on. This is what the DF Robot motor and ESC combo looks like. Just wanted to show you as a size comparison. The Bristol Bot Builders ones are pretty much the same overall footprint, but the connector on them is way smaller, and I suspect they weigh a bit less. So this is what comes with the DF Robot motors. We get this much longer cable. That's 3 grams. That's already more than 3 times as heavy as what comes with the BBB kit. And then we have the motor itself, 10.41 grams with its board. I'm going to quickly desolder this board and solder on one of the Bristol Bot Builders boards so I can do side-by-side comparison. Boom. Alright, now you can see this is lighting up, which means that it is being powered. This is the transmitter. So if I push the sticks on here, things do spinnies. So you can see everything's working just fine. It's close to what a full charged 2-cell would be. You can hear it gets a bit faster. 10.5 volts. Let's try 3-cell nominal 11.1 volts. So this would be a 50% state of charge 3-cell battery. No. Yeah, when I go from forward to reverse, now the DF Robot speed controller is no longer cooperating. Bristol Bot Builders one, perfectly happy. So I think that tells me I would kill this if I kept going, but the Bristol Bot Builders one seems to handle it just fine. So I'm gonna unplug the DF Robot one. And now let's try a full 12.4 volts, which is a fully charged 3-cell LiPo. In fact, I'll go even a bit higher, 12.5 volts. If my speed controller, or if my receiver doesn't die at this, I'll be surprised. So now we're running just the Bristol Bot Builders guy, 12.5 volts. Perfectly happy. I mean, the motor might not be for very long, but the speed controller can totally handle it. I'm impressed. Well, I guess you'll see if something exciting happens here. Yeah, you see that? Little sparky bits shooting out of the DF Robot speed controller there? Yeah, it didn't like that. This is what my recently blown up speed controller looks like. Might be kind of hard to see, but there's like a big black dot there where there's a burn mark, and there's some blackness all over the crap here, so not good. This was not designed to operate at 12 volts. So this is Division. Division has a big fuck off vertical spinner. That is Division's MO. It has a big fuck off vertical spinner. The needs of this spinner are to do two things. Number one, it needs to spin very, very, very fast. And number two, it needs to have enough torque to do this. That dictates the motor, more so than the speed. Any motor with the same kV rating on the same voltage will give you the same speed. But most motors will draw so much current that they will heat up to the point that they just start to melt their windings. If you get a motor that isn't designed to take currents like 40, 50, 60 amps, and you try to draw enough current to lift an entire robot's weight with its fricking weapon bar. Now obviously I also have a gear reduction, or that's pulley reduction, so I'm using a belt that drives this weapon at about a third the speed of the motor. But the point remains that I still need a ton of torque at this motor. So I chose a really big beefy motor that has a high current rating, and when it's drawing that kind of current, it won't melt. Now for the drive system, like I said before, I'm using those dinky little 1806 motors. Obviously this is not a very drive focused robot. It's not meant to push other robots around. It's meant to launch them into the frickin' ceiling. So I don't need to use a motor this big for my drive system. That would be a stupid use of weight. Instead, I use the much, much smaller, lighter weight 1806 motors, and I can get away with that with a high enough reduction of 15:1 through my custom gearboxes that you can find on my web store, by the way, just a free design, I don't sell them. And that allows me to be able to drive around just fine, plenty of speed, plenty of power to move around. I have a little bit of pushing power, but I mean, even with these wheels, you can see they're just designed to move the robot around. They're not designed to push things. Shrapnel mine's a different story. The weapon is a saw. It's a much smaller diameter saw. This is a 7.5 inch diameter weapon. This is a 2.25 inch diameter weapon right now. I might be making this bigger in the future, but it's not very big. And it doesn't have to be big because it's a saw. And it's designed not to store kinetic energy and dish it out in one hit. It's designed to cut through things. So it's gonna have a bunch of little teeth on it. This is just a test disc. The actual saw blades, like this one, obviously are designed to actually cut things. I was just testing this with some high-speed filming to get a better sense of if it's actually spinning the speed that I thought it would and how fast it spins up, etc. But this is what the actual saws will look like. The idea is to cut things. So I care way more about speed than I do about torque with this one. So I'm okay with getting a motor that just runs fast. Now I'm using a 2-cell battery with this because the servo that powers this arm, this blue thing here, it can't take more than around 8 volts. So 8.4 volts from a fully charged battery is about the maximum of what this can handle, and that dictated the voltage I was running everything else at. With Division, I've run it at 3S and at 4S in different variations. But right now I'm running at 4S, so I switched from a 3000 kV weapon motor to an 1850 kV weapon motor to get similar speed at that higher voltage. Whereas with this guy, I knew everything was going to be at a low voltage, so I need a higher kV motor. So I'm using a 2600 kV, 2600 kV motor for the weapon and for the drive. And I had to make a trade-off with the drive because I really want pushing power, but you simply can't get a ton of pushing power when you don't have a high reduction, like with a 15:1 that I have in here. So instead of using a dinky little 1806 motor and a 15:1 reduction, I'm using a gigantic motor and a much smaller reduction of 2.6:1 to keep the cost down, and also to allow me to use really big beefy steel bolts as the shafts. I mean, there's lots of different things that drove the decision to go with this for the drive system, but at the end of the day, by using a motor that can supply a lot more torque, even at a lower reduction, I get pretty similar, if not better, pushing power, and by using big wheels, I have enough grip that I get way more pushing power out of this guy than I'll ever get out of Division, even though its drivetrain is geared down in a way that's more suitable generally for pushing. So those are just different trade-offs. And then with the saw blade,
I mean, I didn't know what the ideal cutting speed for a saw is. I did some Googling. I saw that some circular saws that are around this size tend to run around 20,000 RPM, and I said, sounds good to me. So 2 cells, 2600 kV. That's right around 19,200 to 20,000 RPM. And that's what I get. And that's perfectly sufficient for my needs. But I don't know if that's the ideal thing. I'm just doing what I figure might work. So you can get an idea of like what the different considerations are. Now, yeah, when it comes to the torque for this motor, I don't really know what the torque needs are, but if it works, then I assume it's good enough. And if it doesn't work, then maybe I'll have to upgrade to a bigger one. A lot of combat robotics is iterative design and trial and error. You're never going to get everything perfect on your first try. It just doesn't happen. So you're just going to have to live with the mistakes that you make and learn from them and make the changes required from what you learned in order to make it work the next time. I know this was a long one, so shout out to you if you're one of the 4 people still watching at this point in the video. If you liked this video, make sure to hit like. If you want to see more videos like this, make sure to subscribe and hit the bell icon for notifications, and make sure to look for my next video coming out soon. Thanks for watching.